Have you encountered the Bland-Altman method, sometimes also called the Bland-Altman plot or analysis? If you have, let me know in the comments. So developed by statisticians John Martin Bland and Douglas Altman in 1986, they published it in the Lancet. This is a method for assessing the agreement between two measurement methods. Now, does that make sense? So this is to do with your measurement itself, the techniques you're using for the measurement. It's not just whether they correlate, but whether they can be used interchangeably. Are we on the same page? We may not be on the same page because if you're like me, you're probably thinking, but we have like the t-tests, right? And then we have these analysis of variance. Why do we need this other one called the Bland-Altman test? Hold on, let's get right into that. So instead of simply correlating two methods, as seen, does this method correlate with that method? This apparently can be misleading. So the Bland-Altman test or method plots the difference between your two measurements. So method A minus method B. It plots this on the y-axis against the mean of the two measurements on the x-axis for each subject. Are we on the same page? When it does this, what you get is the bias, and the bias is the mean difference. So this is the average systematic difference between two methods. And this should ideally be close to zero, meaning there should be no difference if you want to be able to use those two methods interchangeably or two techniques interchangeably. You also get as an output the limit of agreement, LOA. And this one is the mean difference plus or minus 1.96 times your standard deviation of the differences. Have I lost you? What this whole mean difference plus or minus 1.96 times the standard deviation is doing is representing the range within which 95% of differences between the two methods are expected to fall. So you measure and have a grasp of the range where if you were to repeat the test 100 times, 95% of the results would be. You really don't want to use any of the tests you may have heard of already, such as your Pearson, the R correlation value, because it turns out that two methods can have a high Pearson R value, but still disagree badly in clinically meaningful ways. So that's why you need something like the Bland-Altman, which reviews the magnitude and direction of disagreement. The ideal situation is that you get a small, non-significant bias and you get a narrow limit of agreement. Are we on the same page? What you will notice is that you will have a scatter plot, and here you don't want to see obvious patterns in the scatter plot, which would suggest proportional bias or heteroscedasticity. And what heteroscedasticity means is, so here, let's use an example. Imagine you and your friends are throwing paper airplanes, and you want to see if how hard someone throws it affects how far the plane goes. You would think so, right? But here's the thing. When kids throw softly, the airplanes land in almost the same place every time. But when they attempt to throw really hard, the airplanes land all over the place. So there isn't a consistent place that they land. Some land super far, some not far at all. So that changes the amount of spread you're getting with the amount of effort that you apply. And this is heteroscedasticity. It may make more sense if you think that there is such a term as homoscedasticity, and this is where the data points are spread out about the same everywhere. But where we consider heteroscedasticity, the spread changes depending on the situation. You may not have encountered this yet in your common statistics discussions because these tends to be applicable in clinical method comparison studies. So where you're comparing a new diagnostic device to a gold standard, for example. For example, two measurement methods of the same variable may be explored. So say you have an intrusive measurement system and you want to compare that with one that is less expensive or less intrusive. Let's pick temperature measurements, for instance. If you have a current method, but then one that is promising to be quicker, less expensive, and less likely to cross-infect, then the researchers will be willing to adopt the new method if the temperature difference from the current method is no more than, say, 0.8 degrees Celsius. To determine whether there is agreement, you have, say, the measurement of 100 patients taken using both methods in immediate succession, and then you record these as pairs on a spreadsheet. In the Bland-Altman plot, the new method can be set as method 1 and the current method that you're comparing it to as method 2. How you would do this practically, say you have one method where you're using a digital thermometer to measure temperature, and then you're comparing it with a second approach where you use an infrared thermometer. So you get some data outputs based on that. Say you did it for 5 people in this instance. The first analysis you would do then is to compute the averages of the reads that you got based on each type of method. So for the digital one, you can see you have 36.8, then one read at 37.1, then one read at 36.5, and the other 38 and 37.4. For the infrared, the first person read with the infrared approach at 37 degrees, then it was 37.3, 36.4, so on and so forth. So now we're going to do the averages. Are you ready for the averages? Let me know in the comments if you are. How you calculate the averages for this is that you will take person 1, you will add their results together. So person 1 for the digital got 36.8, but then for the infrared got 37. So here you just add them together, divide by 2 because you've got 2 observations. You do the same for person 2, person 3, 4, and 5. But then there's something else we have to do in this instance, and that's to look at the differences of the output between the digital as well as the infrared. We are still following, right? So what you do then is your 36.8 with the digital thermometer. You take away what you got for the infrared, which was 37, and so you actually have negative 0.2 as the difference for person 1. And you do the same for all the other individuals. So what you end up with is a differences output. Now, who knows what comes next? So we're going to plot these points. The x-axis is going to have the average temperature that we measured, not the individual reads, but the average. And then for the y-axis, we're going to put the difference that we've calculated. Are we following so far? I like to check because when you're doing complex things like this, I'm not just going to run through it and assume we're on the same page. If I've lost you, let me know in the comments where I lost you. So now we have to do something quite unusual, which is to calculate the bias. And basically here we have to get the average of the difference. So quite unintuitively, we're going to add together all the differences. So the negative 0.2, the 0.1, the 0.3, the negative 0.1 will all be added together. And then you divide it by the number of observations, which in this case, we did 5. And you notice whenever it's the negative value that we got, we put that in brackets so that the computation can happen. Have I lost you? So then we get this output, which is negative 0.02. And so it turns out then that the bias is approximately negative 0.02 degrees Celsius for this temperature measurement. So how we're going to interpret it is that the digital thermometer reads slightly lower on average than the infrared thermometer. But the bias, as you can see, is very small. I don't know if any of you watching can tell me what the next steps are. But the next step is now to look at the standard deviation of the differences. And as you know, if you're using Excel, you can actually just use the formula that pops up to measure the standard deviation of the differences. And suppose we get 0.23 degrees Celsius. Are we on the same page? We have another step, and here we want to look at the limits of agreement. So that's the bit where we talked about the difference plus or minus 1.96 multiplied by your standard deviation, which we've calculated. So we've looked at the differences already, and we've now looked at the standard deviation. So we're going to put this value of 1.96 because we want to capture the range at which 95% of our data falls. For those of you that have done stats before, I'm sure this 1.96 you're familiar with, so you can let me know in the comments what this 1.96 is about. So substituting the values, we get negative 0.02 plus or minus 1.96. We're multiplying by our standard deviation, which is 0.23, and so we end up with a range. So we get 0.02 plus or minus 0.45. And what that equates to then is an upper limit of agreement that is 0.43 degrees Celsius and a lower limit of agreement that is negative 0.47 degrees Celsius. Did we all get here together as a group? If not, let me know in the comments. So how we interpret this is that most differences between the thermometers fall between negative 0.47 degrees Celsius and 0.43 degrees Celsius. So if clinicians consider 0.5 plus or minus acceptable, then the two thermometers may be used interchangeably. So at this point, I'm expecting you to ask me a question. Ask me the question, where can you do this plot? And to that, I'll say, I'm glad you asked. You can do this plot in Excel. You can use Python to do the plot as well. In Python, you can use the matplotlib and the stats models, or you can do it in R. There's Bland-Altman. You can do it in SPSS or in GraphPad Prism. So that brings us to the end of this video. Thank you for subscribing, and thank you for giving the video a thumbs up whenever it is useful to you.